Greetings and welcome to this lecture regarding column analysis and design from a mechanical and somewhat structural engineering perspective. We specifically want to focus on the compression of long components. That's what a column is, a long component in compression, how they fail, why they fail, and how to reduce that failure. So, a little bit of background. Columns are used in architecture from a long time ago, in ancient times, as you see on the Parthenon here. This is thousands of years old, and these columns are still standing. Pretty amazing stuff. I would like to know how they even got them up there, much less put them in such a precise arrangement. Modern times, we still use very similar types of columns. Now, this was built about 100-something years ago, but even then, there's this structure that was built about 50 years ago. And there's still columns being used to support this cantilevered roof over this walkway down here. But a lot of the design principles have not even changed over time. The ancients, even without the analysis that we had, realized that the centers would buckle, so they would make things larger in the center rather than at the top or the bottom. Now, these did not use that. This is reinforced steel columns here, and these are concrete, more for the aesthetics of the facade. And yes, they were here to hold this up, but they didn't need to have that strengthening in the center. Now, we even have commercial uses, maybe things you didn't think about. For example, well, these are actually columns. Each one of these is a column holding up the material above it. Well, this one collapsed because it wasn't properly strengthened. It probably didn't have anything inside it that was holding the sides out, so it buckled right here. And here's a tie rod for a car, I'm assuming. Here's what it's supposed to look like, and this one was bent. Bent tie rod is pretty common in racing and some other high speed, high stress uses for the automotive industry. So these kind of failures can take place, and they do quite often. Medical application, something I'm a little familiar with. We use columns and surgical tools. Here's a surgical tool that is a scissor, and as this moves back and forth, a rod inside moves back and forth, moving these blades back and forth, and as the rod is pushed into compression, it becomes a column. You can even model bones as columns. This is obviously a broken femur, but it is a long structural member in compression. So as we try to understand how these bones can be fixed and how we can improve some of the things that we do in the surgical realm, then we need to understand how they work in the physical realm. So what makes a column different? Well, again, a column is different because it's long, and that length gives it a different failure mode of buckling. Well, when you say long, we don't necessarily mean long. I mean, long is a relative term. So is long 2 inches or is it 2 yards? Well, what we really mean is by using the term slender. So because it's slender, which means there's a certain ratio of its length to its width, I'll get into that in a bit, that makes it more unstable. And so it will fail before it gets to its force over area, the yield strength. So we have to consider some more complicated issues than just force over area. So what makes it slender is we can measure this. The slenderness is the ratio of its effective length to the distribution of its cross section. Well, what do I mean by that? Well, we have to do some analysis with that. So we actually have a slenderness ratio, otherwise known as SR, and it's equal to KL over R. Now, this K thing we'll talk about in a second, but L is the unsupported length. R is the weakest radius of gyration. We calculated the radius of gyration in a previous class, but I'll definitely review it here. And K is the end fixity factor. The fixity factor depends on how each end is connected. So if it's very rigidly connected, the fixity factor becomes lower, reducing our slenderness. And there's a difference between the theory and the practical of that fixity factor. So let's go into that a little bit more. So we have a bunch of different fixity factors here. If you have the two ends of your column and the loads coming down on top here, assumingly, then you have a column that will buckle out like this. But this end won't move and this end won't move. So it's very rigid and allows for a lot less mobility, which means that our fixity factor is low, reducing our slenderness. Well, if you put a pin at the end here instead of fixing it in there, our K value becomes a little bit higher, increasing our slenderness and our instability. And these two here both have K values of 1.0. This is where the end is fixed in rotation, but it can translate somewhat. Maybe it's on a roller or something like that. Then over here, it's pinned. So you've got a pin on the bottom and pin on the top. This is often how we model a lot of our long compression members, say they're in a truss or something like that. This is a conservative way. Even if it's kind of fixed in place like this, you might consider using this K value just to be conservative. Then this is the more traditional flagpole, where you must consider that this is a free end that can move around, but it's fixed on the ground here. Now here, it can't move too much. Again, it might be on rollers, but on this end, it's pinned. So we have a much higher K value here. Now, these are the theoretical ones. These are developed using standard analysis tools. But when we look at what actually happens in the real world, if you're going to design, this is what you should be using. Okay, let's look at that radius of gyration. How do we calculate that? Well, first off, it's a measure of how distributed material is away from a central point. So if you have a lot of material, but it's all concentrated in the middle, it won't have a very high radius of gyration. But even less material at a very decent distance away from the center will give you a high radius of gyration for the amount of material. Usually, considering we're talking about a cross section, you're talking about the area. So it is calculated R equals the square root of the area moment of inertia divided by the area. Now again, we want to look at the smallest r because that will show us our weakest position, and that will show us the direction in which the column will buckle. So the area is going to be the same no matter what. What's going to be different is the area moment of inertia. So you're going to want to look at the various axes, usually just x and y, but you might find something different if you take a different axis. But you want to look at the smallest I so that you can find the weakest R so that you know what your critical load is going to be. Of course, area is a cross-sectional area, and as we mentioned, use the smallest or weakest R if everything else is the same. Continuing on this column analysis, it begs the question, what about the materials? Because all of that we were just looking at was geometry. Well, what we want to calculate here is the column constant, sometimes known as the transition value. Column constant is calculated using this formula. The E is the elastic modulus and SY is the yield strength. Notice how the slenderness ratio is geometry driven and the column constant is material driven. These two things together will help determine what failure mode we will see, and therefore what kind of loading we can expect to support. Now, what happens if we have a particularly long column? How do we know if it's long or not? Well, we compare these two values, the slenderness ratio and the column constant. And if the slenderness ratio is larger than the column constant, then we refer to it as a long column. We're going to use the Euler formula. Now, the Euler formula was developed by Euler many, many years ago, and it looks like this. Now, if you'll notice, this formula here is equivalent to this formula here. That's because if you do this SR, which is KL over the radius of gyration, and the radius of gyration is a square root of I over A, but you have to square it, that means you'll get I over A. So if you do that here, you cancel out A and you end up with I. So that's why these two are equivalent. It depends on what might be easier for you to calculate. When you graph the slenderness ratio with respect to the critical load, you get a curve that looks something like this. This uses critical stress, but of course it's just divided by that area, so it's going to be consistent all the way through. So you can see that as you have very high slenderness, you have very low critical load. In other words, it doesn't take much to make it buckle. As your slenderness becomes less and less, your critical load becomes higher and higher. So that just makes sense. As it gets shorter, then you can put more load on it. But notice how if you had it really, really short, you should be able to put an infinite amount of load on it, which makes absolutely no sense. So what's going on here? So let's move on to the next part and we'll be able to answer that. Well, as you can see, a long column has a large slenderness ratio compared to the column constant. Well, this is when we have a small slenderness ratio with respect to the column constant. So that's what determines whether it's an intermediate column or not. And we use what's known as the J.B. Johnson formula. And it's equally strange, where we have a critical load equal to the yield strength times this crazy thing times the area. Now, if we want the critical stress, we just divide by the area. We get rid of the area here. So what does that look like on a graph? Now this puts the Euler curve in the same graph. So if we take that Euler curve, we see it going up infinite with a relatively small length, which doesn't make sense. But we have the Johnson formula that starts here, goes to here, and meets that Euler curve right about here. This spot here, the transition point, this is where the column constant is equal to the slenderness ratio. So we have the Euler curve coming up to this point, and then material factors start taking more of making more of an impact, and we end up finally at this point, and this point is where the failure stress is our compressive yield stress, just force over area. Okay, so we now know the difference between long and intermediate and why those are important, what the factors are, and how to analyze them. Now moving on towards column design, one of the most important considerations is whether you're involved in a structural application. The first and last word of a structural application, say in a building or someplace where people are living and working, is that you use the relevant governing body codes. The governing body go by the different materials, and they will have similar calculations to what we just showed you, but unfortunately they get rearranged, they get renamed, they have their own notation. So one will use F, one will use S, one will use sigma, one will use omega. It's kind of annoying, but it's something that you really have to learn to do if you're going to be dealing with structural applications. They're usually more complicated in terms of the formulas, and they use a whole lot of tables as well. There are large books dedicated to these things. So, for example, if you're going to be dealing with structural steel, you want to use the AISC codes, and they can be found in this bright red manual. Another example is that they use a slightly different value instead of CC. If you're in my class, we'll go over some of those things in the class, but just remember that if you're going to be using structural steel for structural purposes, you better use the AISC codes. What if you're using aluminum instead? Well, you use the Aluminum Association codes, and their method's a little bit different. This is what their design manual looks like. And their approach uses these kind of general formulas, and then you plug numbers in that are based on the different alloys. So the good thing about these types of codes is that if you know how to use them and you use them appropriately, then you can't go wrong. So you don't have to do a whole lot of guesswork. You just follow the procedure and you know that you're doing the right thing. When it comes to structural wood, I had to use this in a project of mine this past year, and you use the American Wood Council National Design Specification, and that looks something like this. And going through that, they still use effective length and the slenderness ratio. Those things are still applicable in all of them. They just might be called something different, and you'll still do those kind of calculations, and then there's more to go beyond that, and it often gets complicated for any of them. Along those lines, though, if you don't have a code to go by and you're doing some general machine design, you want to probably use the Euler and Johnson theory. They do pretty well, but you'll want to start using a higher factor of safety. So start with 2.0, depending on the application. If you're dealing with human life or something else, you're going to want to have a higher factor of safety and so on. Moving on to other aspects of the design, we want to know what kind of shapes we should use in the design if we're going to be designing something from the bottom up. Well, let's look back at the theory that we just covered. If you look at the slenderness ratio is preferred to be very low. The more slender it is, the more likely it is to fail in buckling. In fact, the AISC strongly recommends not using a slenderness ratio of over 200. So we want to keep our SR to a minimum. So we want to have a low K. So if you can fix those ends better, then do so. We want to have low length. So if you don't really need a long length, then minimize it. You might be able to support the length in various ways, and that will reduce this L. Or you want to have a high radius of gyration. So if you can simply choose a cross section that has a high radius of gyration, then you'll keep your slenderness ratio fairly low. So that radius of gyration again is the square root of I over A, and in order to achieve this, you'll want to have a high area moment of inertia with all of the axes, not just one, because it's the weakest axis that's going to determine your critical load. So you want to have that high I 360 degrees across all the axes. That means you want to push that material as far away from the center. And what does that look like? That looks like a large cylinder. So a large cylinder, that's why so many columns are cylindrical or circular in general, because that is the most efficient shape for a general freestanding column. Other shapes are relatively efficient for columns. So square shapes are a great example. They're very economical, very common. They might be more useful. They might be aesthetically pleasing. Let's see what some of these other shapes we have are. So notice how the square tubing and the round tubing have hollow insides. That's because material in the middle is relatively useless in terms of what you have going on here. In fact, it doesn't give you much eye at all and increases your area. So it really does not help your radius of gyration. So these wide flange beams are actually pretty good. Because they have wide flanges, they push a lot of material out, in this case to the right and to the left. They obviously have a lot of material on top and bottom, so they're very efficient that way. But they're pretty good right and left. And so in certain situations, it might be very good to use these, and they might have other advantages, such as being able to be easily sourced or have great connection points. Because you can imagine that putting other beams and joists in here, if this is in a column, is a lot easier to do than if you had a round pipe. So that may very well be excellent reasons to use a wide flange shape. And also, if you are building a structure that has supports that are coming off the insides, if you will, of this W shape, then it is supported in the middle. So you'd really start to consider the other direction, the strong direction, as where it's going to buckle, because the weak direction is supported. You can also create built-up shapes that work to your advantage, then using the same basic idea of pushing the material far away from the center. And as I mentioned, supporting that one axis will work out very well for a W, an S, or some kind of I shape here. Okay, in review, columns are special because they fail in buckling, not in specifically a material compression failure, as you might consider in a short compression member. Now, what are the factors that affect this failure? First off, how the ends are fixed. After that, are there any supporting structures that could stop this from bowing from side to side? What's the cross-section geometry like? Does it have that material pushed out to the side? What's its radius of gyration? What are the material properties? We need to cover yield strength. We need to cover the modulus of elasticity. If it's stiffer in terms of modulus of elasticity, then it's going to be less likely to bow out like this. And what is the load that we need to support? The behavior of columns shows the interaction between the geometry and the material and how they're limited. Geometry can only do so much and the material can only do so much. And we see that in those curves where you've got the Euler curve that is heavily influenced by the geometry, and the J.B. Johnson curve, which is more influenced by the material. And those long columns, again, those are governed by the Euler formula, and the intermediate columns are governed by the J.B. Johnson formula. They meet at a transition point, and we've got to figure out which of these two to use based on our formulas for the column constant and the slenderness ratio, and which side our column is with respect to that transition point. When we do structural design, we have to go by the relevant codes. They've got similar analysis and they use some of these things, but they're usually more complicated and might take longer to figure it out, but you'll be sure that you're doing the right thing. If you happen to have unsupported columns, they're best made using cylinders, squares, or W shapes. Those are more efficient than the others, and so you don't have to use as much material to get a very strong column. If you happen to have supported columns, well, then you could use a variety of shapes. Or maybe you don't have a very heavy load, you could use something that's more workable for some of the other important things of your design. And don't forget, you have to consider the weakest unsupported axis. And I'll be following this video up with another one that goes into some of those issues. Finally, I wanted to mention a couple of examples here. This is an interesting picture of a column. Notice how this is failing in the direction that we are facing, not left to right, but forwards and backwards. This column is a wide flange shape, but it is weakest in that plane. So it clearly shows right here that it kind of flared out, it was buckling over in the weak plane. These columns look like they're doing pretty well, but this building, the Citicorp Center in New York City, was originally designed and built to accommodate this, believe it or not, it's a church right over here, and they had to build it over it. So they came up with this stilt type structure. And one of the biggest issues with any building is that it has to withstand wind loads. They considered the wind loads hitting the face here and here and here, the four different faces, but they did not consider it hitting the corners. They had already built the structure when someone pointed this out to them. So very quickly they had to go in and buttress a lot of work. Obviously this is highly dependent on these columns. So I really hope that your designs, when you get to them, don't end up like this, or if you find out you're in trouble, that you get lucky like these guys did. Well, I hope that this video has helped you understand columns, that you will use this in your future endeavors, and thanks for watching.